We are going to see at the conceptual level. We won't be giving much importance here because we will be doing it practically. So when you do it practically, you will know what exactly is routing and switching. But anyway, let's just briefly take a look. So routing is a process done by routers, right? As an instance, and it's the OSPF model. It's something that it's a process that happens in layer 3. Right? Physical, data link, and what? Network. It happens in the network layer. Okay. So basically, your network is supposed to be like this, right? So this is how your network is. So you have a router. Each and every interface of a router is a network, and that's why we did the subnetting, right? So you will give each and every network to one portion, right? So like this, if you imagine at a bigger level, so you will have hundreds of networks. Okay, hundreds of networks. So one particular client may want to reach to a particular network. So how will it go? Right? By default, you know the router knows only the connected interfaces or the connected networks. They don't know about other networks. Okay, so this is a process called routing, in which the routers they learn. Okay, the routers they learn information on how to reach other networks. Okay, what are the paths they can follow or they can use to reach a particular destination. Okay, destination can be, say for example, 100.20.20.0 network. So that's a destination. Okay, so let's say this client wants to go to the destination. So it's not a local network, so it will contact its gateway. So in the gateway there will be something called gateway router. Right? Router is a gateway. So gateway and router are similar or same. So a router is supposed to have something called a routing table. So in the routing table there will be an information regarding how to reach that particular destination. If the routing table lacks that information, then you will simply get a message, host unreachable. Okay. If the routing table has the entry for the destination and it reaches the destination, it forwards to the other router, but you are not getting the reply, then you will get request timeout. But if you have the destination entry and the destination is reaching, the destination also knows how to come back, then you get a successful reply. Okay. So that's what basically routing is. Okay, routing is all what routers do. So routers they learn the networks, learn about the networks, and they add in the routing table. Now, if you say, for example, if you take a simple network like this, so what network? How many networks are here? It's a very simple network. How many networks do we have here? Provided every interface of a router is a network. How many networks we have here? Like when you subnet, how many networks you have? 4 or 2 or 3?
You said something earlier about an interface.
Interface.
Network?
Every interface is a network.
Okay, so that makes it 4? Oh wait, S-O-E. Would it equal the rest?
You see, its IP is also plotted here. So every interface, so this is an interface. Interface means port, huh?
Okay.
So this is a network, this is a LAN, you can say. And this is a network. Right? So this is an interface, this is an interface. So this is another network. This is another network. You have 3 networks. Okay, you can say these 2 are LAN because you have computers here, devices here. And this is a point-to-point network. You want network IDs, you can say, let's imagine /24, okay? Subnet mask. So this is 172.16.10.0 network. This is 62.1.3.0 network. And this is 192.168.100.0 network. Okay, so here it will be 100.1, 100.2, 100.3. Here 3.4. See, okay, this is I think. Sorry, how come 62.1 63? I think this is wrong, something wrong here. I think maybe in the middle there may be a lot of other things. Okay, so whatever it is. Okay, let's imagine 62.1.3 network. Okay, don't look at this one. So whatever it is, by default, what does a router knows? A router knows only about its connected interfaces by default. If you don't do anything, okay, you just connect them. So as far as now, if you see router 1 only knows about 172.16.10.0 network and 62.1.3 network. So this router 1 doesn't know about 192.168.100 network. It doesn't know. So if this computer has to reach this computer, let's say this computer's IP address is 100.10. Okay, it doesn't know how to reach. Because if it has to reach, it will contact the router will simply say, I don't know, unreachable. Okay, so now you have to feed the router, you have to teach the router. Now you can do it in two ways. One, so this is something called a routing table. One, you can do manual configuration, that is static routing. The other one is dynamic routing. Static routing means you will go into the router and you will tell the router that if you want to go to this particular destination, you have to contact this router, because this router is directly connected to it, or any other router in the middle, which is a forwarding router. That is manually you have to tell. So if you have many networks, each and every network you have to tell, if you want to go to this destination, you have to contact this router. If you have to go to this destination, you have to contact this router. That's manual. Or if you want to do it dynamically, there are many protocols like RIP, OSPF, EIGR, PE, ISIS. So what you will do is you will just turn on the protocols, and the protocols will do the job. So if you turn on the protocols, these routers will start talking to each other. So this router will say, okay, I know about 100.1 network and 62 network, and this router will say, I know about 172.16 and 62 network. They will talk to each other. So that way the routers can figure out the destinations. Okay, so when they talk to each other, so this is how the routing tables will be updated. As you can see, you will have the interface, destination, and the hop. Hop means what? How many jumps it has to make. Okay, now in this case, if this router has to reach 100.0, it's just one hop. Okay, just one hop. Okay. And if you see 0 hops, what does it mean? Now you see here router 1 is about router 1. 192.168.100.0, that is here. Okay. 0 hops. 0 hops means it's directly connected to it. It doesn't have to jump to another router. So every router is a hop. Okay. One hop means there is one router in the middle. When you do traceset, you get the hop count, right? How many hops? Remember the traceset command? Every router is a hop. We have done it. Traceset. You did ping, right? It's like that we did traceset. Traceset means every router will be displayed. If you do trace at google.com, you will see all the routers. This is jumps. Okay, so that's what will be there in routing table. Routing table also have many other things, like let's say for example a particular destination. Okay, so it says you have to go through this interface, this port, and it's one hop away, and there will be something like a cost. Is how much is the cost metric? How much is this path reliable? And all these things, all these factors will be there. Because in a network, if it is a big network, for one destination you will have many paths. So these routing protocols have to calculate which is the best path. So it will be calculated based on the bandwidth, based on the reliability, speed, many factors, delay. Okay, all those factors will be taken into consideration. Okay. So these are the properties of routing algorithms. Hop counts, that's one factor. So these are some of the algorithms or the logic that different protocols use for calculating the best path. best route. Now, we are not going deep inside it. Like see, basically you have two types of routing protocols. Now, if it is a static route, then it's more believable. If you put a static route, if you manually put a route, if you want to go to this destination, you contact this router. If you put it, that is more believable because you manually did it, right? But if it is like there is a routing protocol, then a decision has to be made among routing protocols. So you can have multiple routing protocols configured. Like RIP is one routing protocol, and EIGRP is another one. Okay, RIP follows an algorithm called distance vector algorithm.
Come again, sir?
Distance vector. You know what is vector, right? Speed, distance. EIGRP uses some other protocol. It uses its composite. So let's say, for example, RIP basically uses distance vector. That basically means less hops is less cost, less costly route. More hops, more costly route. So which one will be preferred? Less costly or more costly? Huh? If you want to go to Philippines, which flight will you pick? Same thing, same facilities. Less costly or more costly?
Less costly.
Less costly, right?
Yeah.
So you pick the less costly one. So less hops. But these less hops, maybe you have a less hop one route, and then maybe you have a more hops. Let's say if you want to reach a particular destination, one route says 3 hops. The other route says 5 hops. So it has to surpass 5, it has to jump 5 routers. So RIP will say the one with 3 hops is best, the least cost. Okay, but maybe that one may be just a 1.54 Mbps connection, a T1 line. The other one may be a 200 Mbps connection, the 5 hops one. So it doesn't give importance for speed or bandwidth, RIP. Okay, but if you have the advanced protocol like EIGRP, it considers many things. It considers the speed, load, link utilization, power, reliability, packet loss. All these things will be considered. It will bring everything and put in a formula, and then it will give you the cost. Okay, so you have hybrid protocols and you have a simple protocols also. Right? So that's hops. Okay, next hop means the next router. Throughput. What do you mean throughput? The average rate of message delivery over a communication channel. Means how much successful communications are happening. Okay, like how many messages are passing through, successfully passing through. How many packets are successfully passing through. So it doesn't consider collisions. Okay, so you have a high bandwidth and all, but what if a lot of collisions happen? MTU. Maximum transmission unit. Okay, you have a route which is very fast, but it doesn't support big packets. It supports only, a packet can be only how much? 500 bytes. What if you have another network which supports 4000 bytes? That is better, right?
Yes.
Because more packets, less packets, you can put more data in it. Bigger packets. That's MTU. So how much bigger packets the routers support? Okay. Latency. Latency means a delay. Duration between the time when the data is requested and the time when the data is received. So it's a little bit different from speed. Speed. How do you distinguish speed and there is another thing called delay here. So these are confusing terms actually. Speed. I think this is speed we're talking about. The request time and the response time. The difference between them. Delay refers to the time taken to send all packets across the communication link that exists between the sender and the receiver. All packets. All packets. That means complete communication. Okay. Latency means the duration between the time when the data is requested the time the data is received. So it may be just one packet, the other packet may be on the way. So this is a factor when you speak in phone. So delay is important. You cannot have too much delays. But when you send an email, you can have some delays. No problem. Because email, even if it comes 1 second late, no problem. Right? Bandwidth, that's how much the media is capable of sending, the hardware itself, or how much width you have on the road. Reliability means dependability, whether the link is dependable or not, or it just goes up and out all the time. So those are the things, right? It's static routing versus dynamic routing. So that's basically a choice. Now, of course, you cannot use static routing for if you have a big network, right? You cannot manually feed every destination. Okay? You cannot. So normally we actually use a mix of static and dynamic routing. These are the different algorithms: link state, distance vector, hybrid. Now I'm not going into this now, okay, because we will study this in CCNA. I'm just giving you an idea here. Like there is a protocol called OSPF, it's an open shortest path first. That is a link state protocol. EIGRP is a hybrid protocol. EIGRP is from Cisco. OSPF is, on the other hand, is an open source protocol. All these things depends upon what kind of router you are buying. Okay. And RIP is another version. It is a simple version of simple routing protocol. It just takes the outcomes. And regarding convergence, what is the convergence? All these protocols will differ in convergence time. Convergence means failover. 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 So what is failover? So let's say you have a destination, okay? To reach the destination you have 3 routes. Okay? So the way these routing protocols they work, they differ. Okay, in case of RIP, one route will be used and that's it. The other 2 routes will be backup. Okay, what if the primary route goes down? And then how much time will it take for the secondary route to come up? That's the convergence time. Okay, backup route, that is convergence. Okay, and RIP, now say for example RIP does not do load balancing. See, if you are using RIP, you have one primary route, the other 2 routes are simply just there, they are idle, they are not doing anything. But that's a waste, right? You can use it for something. So that's what we do in OSPF and EIGRP. OSPF does load balancing, but only equal cost load balancing. That means if you send one packet in one line, send another packet in another line. So one packet here, one packet there. Equal cost load balancing. But EIGRP is a hybrid version. EIGRP can do unequal cost load balancing. That means maybe let's say the primary link is 10 Mbps. The secondary link is 200 Mbps. So if you send one packet in primary link and one packet in secondary link, that is also not justifiable, right? Because the secondary link is more capable. So what you can do something called, there is a keyword for that, I forgot. You can say that for every packet you send on the primary link, 100 Mbps link, send 2 packets for the 200 Mbps link. So 1, 2, 1, 2 like that. So that is unequal cost load balancing. So these kind of things you can do in the routing protocol. So overall, the best routing protocol is EIGRP. Okay, EIGRP. Now there are full forms for that. You can see that later. Enhanced Interior Gateway Routing Protocol, which is from Cisco. Okay, EIGRP is from Cisco.
EIGP.
EIGRP. AGRP. Okay, so this protocol is the best, but it is from Cisco and it is proprietary. Proprietary means like Microsoft. If you want this protocol, you should have only Cisco routers. Okay, all your network should have Cisco routers. If you have one router, some other company, you cannot do it. Okay. Whereas OSPF, it's open source. You can have any routers, any company routers, like Linux and RIP also. But otherwise, AGRP is the best. Okay, so that's how routing happens. Now, only when you do practically, you will understand the differences. There are many more actually. Actually, you have separate exams and separate books only for routing. Yeah, next we have switching. So switching is a LAN concept, right? Switches all work in the LAN. You know what is a switch, right?
Yes, sir. It works with the MAC address.
Yeah, it works with the MAC address. So that is, it specifically works on layer 2 of OSI, the data link layer. And we already saw what is CSMA CD architecture. So we use CSMA CD architecture, collision detection. So collisions will happen. You detect it later. And you know how switches are different from hubs?
Yes. Yes.
Right.
Hub is a repeater, and
Hub
switch
just repeats the signals.
yes, and
Just an electrical device. Switch, it remembers the MAC addresses. It has something called a CAM table, content accessible memory table. Okay, you can find it all in here. So just like a router has a routing table, switch has a CAM table. Okay, so CAM table is nothing but which port, what MAC address is reachable through it. Okay, so let's say you have a switch here, right? So you have a PC here. So this PC would have a MAC address, right?
yes.
So that MAC address will be associated with that port. So whenever a PC wants to communicate to that PC, they will give the MAC address of the PC. They will not give the name or IP address.
Yes.
So this is layer 2. Layer 3, they will give IP address. And layer 2, it's MAC address.
Yes.
So the switch immediately knows, okay, this MAC address is connected to my Ethernet, fast Ethernet port number 4. It will immediately forward it. And you know the collision domain, broadcast domain.
It's the main, the FF, and
You didn't study what is collision domain, broadcast domain. You studied it in the A+ book. No? It's the difference. Yeah, it's here. Collision domain, broadcast domain. I didn't tell you this before. I thought I told you. No?
I think
Okay, I will tell you. Just wait. Okay, anyways. Okay, I'll tell you this. This is something difficult to understand. So first you have hubs, okay? And then you had bridges. Okay, bridges or bridge. Then you had switches. So these are 3 devices. Now hub is just an physical layer device. It just regenerates signals. Okay. Now in order to understand the difference between the hub, switch and bridges, you have to understand 2 things. One is a collision domain. Okay, you know what is collision, right?
yes.
Collision is accident, packets getting collided. Domain means
Means
a group,
group.
right? A group. So collision domain means, if I say one collision domain, okay, a hub has one collision domain. That means, let's say a hub has 4 ports, 4-port hub. So 4 PCs are connected to it, and the hub is one collision domain. That means one PC or one device, only one device can send or receive at the same time. That is one collision domain. Okay, only one device can send or receive at the same time. One PC. So if PC 1 is sending something, all the other 3 PCs have to wait. Only after it finishes sending, the other PCs can send. or receive. That's why one collision domain. Okay, and one broadcast domain. One broadcast domain. So what is a broadcast domain? So broadcast domain basically means what you know broadcast, right? Broadcast. There are three types of communication in the network. TCP/IP network: unicast, multicast, and broadcast. Unicast means one-to-one. One-to-one. If I'm just talking to you, that's unicast. Okay. Multicast means if I'm talking to a group, like I'm talking to only you three people, that's multicast. Broadcast means one to all. If I'm talking to everyone, so right now I'm doing a broadcast. Okay. Whether you take it or drop it, but I'm doing a broadcast, right? So that is broadcast. So one to all. Okay. So broadcast domain means how far the broadcast will go. How far the broadcast will go. Okay, so if you have a network, I better show a diagram. If you have a network, the only device that's going to stop a broadcast is a router or a router-like device. Right, as you can see here, you have a hub, you have a switch, you have a router. Okay, now in the whole of this network I can say there are three broadcast domains. Because the job of a router is to stop the broadcast. That means if this PC is sending a broadcast, that broadcast will hit this PC, the switch, and it will hit the router and it will stop. It will not go beyond it. If this PC is sending a broadcast, it will hit only this router. It will not go beyond it. So this is one broadcast domain. Right? So how far the broadcast can go. Right? So now I'm doing broadcast, it's only to this. So this class is a broadcast domain. It's not going to the other class. How far? Whereas a collision domain is how many devices can send or receive at the same time. Collision domain. Okay, collision domain. This is one collision because it's a hub. It's one collision domain. Collision domain, you cannot see graphically. So collision domain basically means how many devices can send or receive at the same time or simultaneously. Okay. How many devices can send or receive at the same time? Okay. In case of hub, only one. So only one device can send or receive at the same time. Broadcast domain, how far broadcast will reach. How far the broadcast will reach. So they are totally different perspectives. So broadcast. So actually, broadcast domain is like one group. It's basically groups. So two perspectives. Broadcast domain, how far the broadcast. So till the router, everything is in one group. Collision domain, how many devices can send and receive at the same time. So the difference comes in these two things. Actually, the collision domain. In hub, it's one collision domain, one broadcast domain. Right. In case of a bridge, it depends on the side. How many sides it has. Okay, how many sides it has. Let's say if it is a two-side bridge. Okay, if it is a two-side bridge, okay, then it has two collision domains. That means two devices can send or receive at the same time in each side. One on the left side, one on the right side. Okay, but not on the same side. Two devices can send and receive at the same time. Each side, if it is a four-side switch, four-side bridge, then four devices can send and receive at the same time. Okay, but the broadcast domain remains the same. So only device that's going to stop a broadcast will be a router. Okay, now that's why. So these two things are outdated now. We don't use it. We use it, but we don't use it, heavily. Switches are the device that we use now. Okay, switches are, how many collision domain, it depends upon the ports. Let's say if it is a 24 port switch. Okay, 24 port switch. So each and every port you can plug a device, right? You can plug another switch also, whatever it is. Then you have 24 collision domains. Okay, you'll have 24 collision domains, and the broadcast domain remains one. So that's the difference between a hub, a bridge, and a switch. So 24 collision domain means if you have 24 PCs connected to it, all 24 can send and receive at the same time without waiting for each other. Okay, and hence you can do something called full duplex here. You can do full duplex communication. Full duplex. That means you have half duplex and full duplex. Okay? The difference is half duplex means send or receive. Full duplex means send and receive. Got it? Send or receive, send and receive. That means sending and receiving can happen at the same time. Because every single computer have their own dedicated path. They don't intermingle with the other computers' path. They have their own highway. Okay, so packets can go and come, but that can result in a collision. Because when the sending happens at the same time receiving happens, then there can be a collision. But you can do it if the computers and such can. But if it is working in half duplex, then there will be zero collision. Right? If the switches and the PCs are working in half duplex, that means only sending or receiving in one road, you'll never have a collision, right? Let's say you are driving and nobody is coming in the opposite direction, you'll never have a collision. Head-on collision. Alright, so that's the broadcast domain and collision domain thing. Okay. In all cases, it's one broadcast domain. Broadcast domain remains one. That's how far the broadcast will travel.